Okay, class, let's all pretend to pay attention. Samirah will now present something about water spinning around or something.
Hi everyone! Today we're going to be learning about the ocean and how it moves weirdly because the Earth can't stop spinning. We'll learn about Ekman layers, motion, transport, and geostrophic motion.
Oh god, she's British.
When wind blows across the ocean, the water doesn't move straight. The Earth rotates, pushing it sideways. This is called Ekman motion. In the northern hemisphere, it moves to the right of the wind, and in the southern hemisphere, it moves to the left.
Is it because of the Coriolis effect?
Yes. Now, let's turn our heads to the board so that I don't have to keep animating our mouths. Coriolis force is equal to 2 omega v sine phi, where omega is the Earth's rotation, v is velocity, and phi is latitude. Only the top 100 meters of the ocean feel the wind. This layer is called the Ekman layer. Boundary layers, including the ocean's wind-forced surface and the friction-influenced seafloor, are where Ekman transport arises, governed primarily by frictional forces and the Coriolis effect. The magnitude of Ekman transport is equal to the wind shear stress over the density times the Coriolis parameter. Here we can see steady-state horizontal momentum equations for the surface of an Ekman layer, where tau x and tau y are components of the turbulent stress vector in the x and y directions. But water can't pile up forever. Gravity pulls it back down, making pressure. Horizontal pressure gradient forces push one way, and Coriolis pushes the other way. This creates balance. That balance flow is geostrophic motion. Geostrophic motion occurs away from the boundaries, in the deep ocean where friction is negligible. The flow is parallel to the isobars, lines of constant pressure. The geostrophic equations of motions in Cartesian coordinate systems are as shown. If we rearrange these, it gives us the geostrophic velocity components in the x and y directions respectively. If we then vertically integrate the velocity components from the surface to the depths where friction is negligible across the Ekman layer, we get the net Ekman volume layer, proving that the Ekman mass transport is 90 degrees of the wind shear stress. In the northern hemisphere it is to the right where F is positive, and to the left in the southern hemisphere where F is negative.
This is how giant circular currents form. They store fresh water and affect oceans worldwide. I hear the Beaufort Gyre can store up to 8,000 kilometers cubed of water.
Jeez, Beaufort sounds like a real greedy guy.
Beaufort isn't a person, Eric. It's a gyre.
I actually have a PhD student working on the Beaufort Gyre. Maybe Samirah can tell us a bit about their work to help us apply what we just learned.
The Beaufort Gyre is an anticyclonic clockwise circulation system in the Arctic Ocean that is driven by a semi-permanent high-pressure system. Because vertical velocity is proportional to the curl of the surface wind shear stress, a negative curl would result in downwelling and a positive curl upwelling.
So which does Beaufort do?
Well, despite there being a seasonal cycle where the winter upwelling occurs due to friction between the sea ice and the ocean circulation, the net Ekman pumping is dominated by downwelling.
So the whole ocean is a giant blocked-in flushing toilet. I'm never swimming again. Someone stop this pumping.
I mean, if we had really strong ice cover, like in the 90s, it would result in less pumping, as there would be less friction moving the gyre around.
Tell us something recent. It's not the 90s anymore.
A big bit of water has come off the Beaufort Gyre, transporting down here, causing huge salinity anomalies. When a gyre gets too big, it naturally leaks out, and in this case, it's pooling around the north of Greenland and moving out and shifting southwards. The Beaufort Gyre discharges packages every 15 years or so, but this one has been accumulating for nearly 25 years, which is significantly bigger than previous.
If all the fresh water is moving southwards towards the Atlantic, what does that end up doing?
I mean, the conditions of the North Atlantic are so different from when this last happened in the 90s. Like, the amount of fresh water we lost in the 90s was so much smaller, and we have an even bigger gyre now and pumping so much more water, so...
Get to the point.
We don't know.
Screw you guys. I'm going home. Cartman! Screw you guys. Home.